Good evening, everyone. Welcome back to, sorry the slide isn't updated. This is the 2020 CISSP Mentor Program. That's my first typo and hopefully my only technical hiccup here today. I'm going to check with the moderators real quick, make sure you guys can hear me and see me okay. Let me know if you can't. I was having a little bit of internet issue earlier, and if I need to turn off video, I can. So we're just going to go ahead and dive in. Tonight we're going to be picking up where Brad left us off last week, and we're going to be getting a little more deep into the technical specifics of some of the things we covered last week. So with that, I just want to cover a quick housekeeping item. Again, the chat really should be focused to topics that we're discussing tonight in the class. Please do behave as adults and respect others. At no time are we going to permit any type of derogatory language or any kind of thing that might be offensive to somebody, controversial subjects, etc. And please, no religion or politics. Would have to hate to kick somebody out of chat for that. So just going to double check with my moderators, make sure we're good. All right, looks like we're good to go. So let's dive into this. So I want to open this up with a quote that I really like from Dale Carnegie, which is, "Knowledge isn't power until it's applied." And so as you've been going through this exam, as you've been sitting through these class sessions, you're gaining an immense amount of knowledge that eventually will be applied. And so what's great about that is what you're really gaining in taking this course is kind of a superpower. And we're going to do a quick check-in. Please do chat with the moderators. Very curious to know how many of you have read through chapters 1 through 5 already. Please let them know any questions you have, and I will periodically check in with the moderators. Tonight we've only got 107 slides, so not too bad. We should be able to get through that in time, maybe even just a touch early. And this is a little bit all over the place, so as we go with this, try to keep up. Remember, things in orange are things you want to remember. And we will get through chapter 5, so that's good news for all of us. Again, just some study tips for you. Try to study in small amounts if you can, 20, 30 minutes, and then do a different activity. Flashcards, practice apps on your phone, these types of things are going to help reinforce the learning that you've received. Taking a nap after a heavy topic is very helpful in retaining information. They've done many studies that sleep does help memory. Writing things down, saying them out loud, these also can be really helpful. And I noticed last week a lot more of you signed up for the study group. Thank you for that. It's proving to be a great resource for the students. It's also a resource for us to be able to see the types of questions and challenges you have. That helps inform us for next year's curriculum. And as always, please do try to get out and get some fresh air. I know that's hard these days with the lockdown, but the more you can get some fresh air in your life, the lower your stress will be and the easier it'll be to retain what you learn. These are the links to the study group. If you have not already signed up for the study group, I encourage you to do that now. And then the practice test from FRSecure.education is a pretty good practice exam. There's lots of them out there. I encourage you to use more than one, but this is a great place to start. Now, having said that, we're going to check for that knowledge by doing a quiz. These quizzes are not from the book, but this is material that you could expect to see on the exam. And so fire away to the answer of how many bits compose a IPv6 address. Is it 128 bits, 96 bits, 32 bits, or 64? And if we remember from what we learned, the point of IPv6 was to give us a larger space of addressing. So the correct answer here is A. It's 128 bits. And that's to accommodate for the extra addressing space. The next question on our quiz tonight is, which of the following is useful to find the media access control, or MAC address, that matches a known IP or Internet Protocol address? Is it the Address Resolution Protocol, ARP, the User Data Diagram Protocol, UDP? I don't know if anyone ever gets that. The Reverse Address Resolution Protocol, RARP, or RARP. I don't even know how to pronounce that one, so I'm not even going to try. Internet Control Message Protocol, ICMP. The correct answer here is ARP. So the Address Resolution Protocol is what is helping to map those IP addresses to those MAC addresses. So the next question is, a spoofing attack at layer 2 of the OSI is also known as what? A, DNS spoofing, B, web spoofing, C, MAC spoofing, or D, IP address spoofing. So what do we know about layer 2 that we remember from last week? If we really understand our OSI model, these types of questions won't trip us up as much. And in this case, it is MAC spoofing. It's the ability to use software to rewrite what the MAC address is that is being displayed and processed. So now this is a fun one. This is not from the book, and I'm going to give you guys just a moment to really think about this. What we're going to do is take this list of protocols, and I want you to map the protocol to its appropriate port. And you can just do that with your mouse and kind of, let us know in the chat what you think. I'm going to give you just a minute to think about this, and then I'm going to show you the answers. Is anyone getting an echo? Is there feedback coming through at all? I see that in the chat. And then also, moderators, is the volume adequate? Audio quality okay? So while I wait for those responses, because there's about a 35 to 45 second delay, I'm going to go ahead and move you through. So the correct answer here is that HTTPS is going to be 137 through 149. NetBIOS is NetBIOS is 137 through 139. Boy, it's been a long day. HTTPS's secure protocol is going to be 443. I kind of feel like Brad from last week, right? You do enough of this stuff long enough, and it's easy to get kind of a little bit confused. So why that matters to you is, as you're studying this for testing, don't worry too much about when you do make a mistake. Just try to learn from it, go back and correct. So again, HTTPS is 443. NetBIOS is 137 through 139. Kerbos is going to be 88. LDAP is 389. And secure LDAP is 636. And you will potentially need to know this for the exam. It is testable. This is, for me, was a little bit one of the harder areas, trying to keep all these names mapped to all these numbers. And so what I did for that is actually what you see on the screen here. Was something very similar to this, where I would make matrix and I would just print them out in Excel sheets and then just try to see if I got the answers correct, and then I'd check to see if I was right or not. So the next question is, at which layer does IPsec operate? Is it at the session layer, the data link layer, the transport layer, or the network layer? So knowing IPsec and thinking back to our OSI model, I don't think it's session. It might be transport, and it might be network, because I don't think it's data link either. And the correct answer is network. So IPsec is operating at the network layer. Now this one's a little bit more of a in-depth question, kind of a bit of a word problem. And as Brad and Evan have both mentioned, when you're presented with these word problems, the easiest way to do them is to kind of pick apart and see what they're really asking, because they'll put extraneous information in the question that isn't necessarily relevant. So let's walk through this really quick. As a senior leader in your IT department, you're responsible for training up your technicians so that they are the best prepared to handle their duties. You are the lead technician and manager, and if a problem cannot be solved, they always come to you for guidance. You keep track of the questions the technicians ask, and at the end of each quarter, you quiz them on the questions that they've asked you about. This technical mentoring has made your network team the best in the business. And below are a sample of the questions they asked you for assistance with during the last quarter. At which layer do network interface cards and drivers convert bits into electrical signals and control aspects of data transmission, including optical, electrical, and mechanical requirements? Now, as you can see, there's a whole lot of words up here that don't have anything to actually do with the question. The question is down here. At which layer do the network interface cards and drivers convert bits into electrical signals, which then in turn also controls aspects of data transmission? So is that layer 6, the session layer, layer 2, the physical layer, layer 4, the network layer, or layer 1, the physical layer. And this is also something you're going to see on the exam where the question is presented with several incorrect but sort of correct options. So in this case, it is going to be layer D, the physical layer. But it's D. Layer 1 is the physical. Layer 2 is not the physical layer. So as you study that OSI model, be on the lookout because these types of questions are going to be present on the exam. I myself ran into multiple handfuls that were structured this way. So just be aware of that, and again, when you're doing the word problems, try to filter for where the real question is. So hopefully you're still with us. Hopefully you're right up to here at Chapter 5 and you're ready to dive in tonight. We're going to be jumping into Domain 4, Communication and Network Security, how to design and protect network security. This is going to be technical in nature. For the non-technical people, this might be a little dry and a little bit of additional learning needed. For our technical folks, try to stay engaged. If you're really comfortable with this material, maybe that's a good chance for you to refresh yourself on this, or maybe even help out somebody if you see them in the chat maybe struggling a little. But really do try to stay engaged because there are little nuances in this that will get you on the test if you're too comfortable with the information. Sometimes we forget things, like you saw me do just a couple slides ago. So we're going to dive into network architecture and design. We'll be talking about secure network devices and protocols, secure network communications, or secure communications rather. Again, this is pretty techy. We're going to start off on page 253 in your book. Give you guys just a half a second to open that, and then we're going to kind of dive in. So if you remember from last week, or I'm sorry, Monday. Gosh, this COVID's really getting to me. I don't even know what day of the week it is anymore. Looks like it's Wednesday. Okay, so from Monday, we talked about WAN technologies and some of the protocols. And now we're going to go a little bit deeper into what's really going on inside those technologies that we talked about. So in the United States, we have what are known as T carriers. These are the transmission carriers, I believe, is what the T stands for. I'll be perfectly honest, I do not remember exactly what the T and the E stand for. I think E stands for Europe and T is because it's the USA and we want to be different. But in the US, T will indicate a carrier, the carrier lines of T1 and T3. And in Europe, those lines are E1 and E3. Now, there are some unique and distinct differences between the US model and the European model, so we'll get into that now. With the T1, you've got a dedicated 1.544 megabit circuit. And that's comprised of 24 64-bit DSO, or digital signal 0 channels, similar to the 24 circuit switched phone calls, right? So that would be a place where you would find this 24-bit digital signal 0 channel. DS1, digital signal 1, and T1 are a lot of times interchangeable. And this is a little bit of a history lesson. There are still T1s and T3s out there. They do exist. You will run into them in your career, but they really are kind of considered traditional legacy at this point with broadband, 5G, these other technologies that are coming out that are kind of getting rid of the need of some of these old legacy systems. Just like a POTS phone line still exists, but you're only going to find a landline at my grandma's house. DS1 is really what it's doing is it's describing the flow of bits. Regardless if those bits are transferring across copper, fiber, wireless circuit, really any transportation medium. A T1 is a copper telephone circuit that carries DS1. So the physical medium is a copper telephone circuit, and what's being transmitted across that is a digital signal. T3 is a bundling. So they take 28 T1s and they group them together in a bundle. And that was done because T1, as you can see at 1.544 megabit, not terribly fast. Very fast for the time that it was invented, much faster than a dial-up modem. But as the needs and demands of the network increased and grew, so did the need for increased bandwidth. And so along came the T3, and that had 28 bundled T1s. And that can have a throughput of 44.736 megabits on the circuit. And T3 and DS3 are also used interchangeably, just as DS1 and T1 are. So now to jump across the pond. So over in Europe, an E1 is a dedicated 2.04 megabit. So if we go back real quick, we see a T1 is 1.544 and an E1 is 2.048. It also has 30 channels. And an E3 is 24 E1s that have a throughput of 34.368 megabits. So T1, 1.544. T3 is 28 bundled T1s with a 44.736. And the E1 is a 2.048 with 30 channels, and the E3 is 24 ones with a 34.368. So why did I beat that horse to death? Because you need to know this. And I wanted to really take that moment to talk through that so that you get that, because that one catches a lot of people. You get confused about which one has which bit, and if they give you one of those questions where it says this could be this or that or this, and one of them is a false answer, that could get you. T1 and T3 speeds are often rounded off to the 1.5 and 45 megabits. We generally don't use the decimal points when we're talking about bandwidth speeds. And then another WAN technology is SONET, or Synchronous Optical Networking. And that carries multiple T-carrier circuits via fiber optics. So it's a different medium that allows to transport the carrier circuits of T1 across fiber. So it converts them from copper over to fiber, and it's a much larger pipe. SONET uses a physical fiber ring for redundancy. So if you've ever heard of SONET rings, that's an actual physical fiber ring that allows for that circuit to have redundancy. Getting a little bit deeper in, we're going to talk about frame relay. So what is frame relay? Well, essentially what it is a way to package the packet data into a frame. And I have a graphic here in a minute that explains it better. But it's a packet switched layer 2 WAN protocol. So that means it's switching the packets around. It doesn't give you any error recovery. So there's no error recovery provided in this protocol. This protocol focuses on high speed. That's the kind of the point of this one, is to get it through as fast as possible, and if errors get through, well, then they get through. There's really no way to resolve for them. Higher layer protocols carried by the frame relay, such as TCP/IP, can be used to provide the reliability that is naturally absent from this particular framework. So the TCP/IP kind of rides on top and takes care of some of those things like errors. You have multiplexes, which are multiple logical connections over a single physical connection. So this is how we create virtual circuits, is by multiplexing. So we have all of these logical connections, not necessarily physical, and we're pushing them through a single physical pipe. And we're doing that so that we can create virtual circuits. And there's a couple subtypes there. There is a permanent virtual circuit, which is always connected. It's almost, as you can see, it's analogous to a real dedicated circuit. So it basically mimics what it would be like to have a physical unbroken wire between your location and the telco provider. And then you have switched virtual circuits. And these set up a call to transfer data, and then once the connection gets idle, it terminates. And so the important thing here to remember are these bullet points, right? You want to understand that frame relay, there's no error recovery, it's focusing on high speed, and frame relay is addressed via the Data Link Connection Identifier, DLCI, or DELC. And that's going to look like this. So here you can see we have the DELC down here, okay? We have our bits below that. And then we have our frame. So we have our flag, our address, the information, the FCS, and the flag. So what this is doing is it's putting some containerization, if you will, some structure to the communication so that it's able to be digested and parsed apart so that we know what's going on. So there's the X25 protocol. It's a little bit of an older packet switch WAN protocol. It was really popular in the 70s through the 90s because it gave a cost-effective way to transmit the data. In the early days of the internet, data was very expensive to move around, and so they really wanted to find something cheaper. The global packet switched X25 network is separate from the global IP-based internet. All right, so these are two separate networks. It does do error correction. However, that error correction can increase the latency on any kind of long link of connection. And then it can also carry other protocols on top of it, such as TCP/IP. Then we have ATM. So the asynchronous transfer mode is a switching technology. So what it's doing is it's using asynchronous time division to do multiplexing, and it encodes the data into really small fixed cell sizes. So we go back here again, look at that here, right? Frame. It's chopping that up and it's creating these small fixed cells. This is not the same as the internet or the Ethernet, which are using variable packet sizes. So ATM cells are going to be a fixed length. They're going to be 53 bytes long with a 5-byte header and a 48-byte piece for data to reside in. SDMS or SMDS is switched megabit data service, and it's an older but similar protocol to ATM, also using those fixed 53. So the big takeaway here is that ATM uses a fixed cell length. Ethernet or internet uses a variable packet size. SDLC and HDLC. So SDLC is the synchronous data link control. It was mainly used by IBM for mainframes and mid-range systems. However, there are many other platforms and vendors that have kind of adopted that. We are seeing it kind of fade out in use and popularity. It is a synchronous, so that's an important distinction, synchronous versus asynchronous. It is a synchronous layer 2 WAN protocol, and it's using polling to transmit the data. And polling is very similar to token passing. And the difference there is that the primary node is pulling the secondary node, and then they can transmit that data when polled. Combining nodes can act as, any combined nodes can act as either primary or secondary. And then SDLC supports NRM transmission only, and we'll see that here on the next slide. The most common place today that you're going to find SDLC is inside of a traffic control cabinet here in the United States. So when you go up to those stoplights, that yellow or green, gray cabinet off to the side is most likely using SDLC within it. So then we have our high-level data link controller, or HDLC. Okay, and this is the successor to SDLC. So as they started to realize some of the limitations to SDLC, they needed something that was going to allow for better stability, and that came in the form of error correction and flow control, as well as 2 additional modes that it could run in, ARM and ABM. The 3 modes of HDLC are normal response mode, so that NRM that we talked about just in the previous slide, where secondary nodes can transmit if granted permission by the primary node. Then we have the ARM, which is the asynchronous. So again, SDLC is synchronous. If you're using the ARM mode of HDLC, you are actually doing an asynchronous response, and the secondary node may initiate the communication with the primary. And then there's ABM, which is your asynchronous balanced mode. And that's a combined mode where the nodes may act as primary or secondary, and they can initiate transmission without permission. Key point here, initiate permission or transmission without permission. Now I want you all to say that 10 times fast, because that's a serious tongue twister. So here's a little bit of an example of what that would look like. So here you see we have the application layer here, we have the state machine, here's the HDLC framer. It's doing packet transmission down, so everything obviously always moves down the OSI to the physical layer, and then it pushes back up through the packet receive to the HDLC framer. So that's just a little visual to kind of help you a little bit understand kind of that flow. Now we're going to get into converged protocols. So traditional non-IP services are all provided on Ethernet and IP. Convergence, just for those that aren't necessarily familiar, it's when the state of a set of routers have the same topology. And they're sharing that topology information about the internetwork in which they operate. So if a set of routers have converged, they have to have had all of the available topology information from each other via the implemented routing protocol. So whatever that routing protocol is that's been implemented, that's what convergence in the router sense that we're talking about means. Some of the converged protocols are the Distributed Network Protocol, or the DNP3. It's an open standard primarily used by the energy industry. On the CISSP exam, when we talk about protocols, we're going to be focused primarily on open standards. There are some Cisco protocols. There are some other manufacturers that have developed their own protocols, IBM, and other such companies, but you won't really have to worry about that on the exam, but these open protocols definitely are going to be there. And the Distributed Network Protocol, it's a multi-layered protocol that can be carried via the TCP/IP. It's used a lot in smart grid technology. So you hear about smart cities and smart light posts and cameras and all these other things. That's what's happening there. It became a IEEE standard in 2010. And it was called the IEEE 1815-2010. That's now since been deprecated. The IEEE 1815-2012 is the current standard because it supports the public key infrastructure. Now I'm just going to pause for a second and check in with my moderators. Looks like having some issues here. Yes, sir. Okay, sounds good. I will shut that down. I'm going to go ahead and kill the video, guys, test. Crack that up. Alright. I'm not even hearing it. Damn it. It's always something with this shit, isn't it? I don't see it doing anything. Did that come through? I'm good. You can hear me good? All right, excellent. Sorry about all that, guys. It's been just a wonderful journey into network instability, which then leads to all kinds of problems. So hopefully this isn't too terrible, and I think most of this would have been captured in the recording, so we'll figure it out. So back to what I was saying here. So the DNP3 protocol really the main concepts here around DNP3 is that the specific DNP3 protocol is going to be at the session, presentation, and application. The transport is going to be TCP UDP. Network is going to be IP, and data link is data link. And then physical could be multiple connections, Ethernet or fiber, so on and so forth. So hopefully that's all working well now, and I sound less pausey and robotic. All right, so storage protocols. So these are going to be the communication protocols primarily used to interact with our storage arrays. So for example, a fiber channel over Ethernet, or FCOE. Fiber channel uses Ethernet. Fiber channel is over IP, which is FCIP, encapsulates the frames via TCP/IP. So again, the fiber channel over Ethernet is using the Ethernet transport mechanism to provide the fiber channel connection. But in the fiber channel over IP, there's an additional layer of encapsulation to put the fiber channel communication in a TCP/IP structure. You also have the host bus adapter. And a host bus adapter, for those that aren't familiar, is a circuit board or an adapter that's going to give you a direct physical I/O connection between a host system and a server or a storage and network device. Generally, you want to do this because a host bus adapter is going to provide you additional process power to allow for higher performance. So that's where you will run into those. Then you have the Internet Small Computers Systems Interface, or iSCSI. And that is another protocol that we're using to, again, connect to and talk to some of these storage devices. They really are network and communication intensive devices. And iSCSI can access the storage devices directly across a WAN, and it uses logical unit numbers, or what we call LUNs. And so here's a kind of an example of fiber channel over Ethernet versus fiber channel versus iSCSI versus InfiniBand. InfiniBand is one of the newer ones to kind of come out, and I'll kind of unpack a little bit of this for you guys here real quick. So here you have the application OS layer and the SCSI layer. And you'll notice a lot in the world of security, we talk about layers, and everything seems to be a layer. So get very familiar with that term and realize it can have very different meanings. So here with the fiber channel, you can see we have a direct connect down to fiber channel. That's going to go between 1 and 8 gigabit a second. We can do fiber channel over Ethernet, and that then goes through a Converged Enhanced Ethernet Protocol. That's this CEE. So it's Converged Enhanced Ethernet. And it's basically, think of it as an improved version of the Ethernet protocol, and what it does is the number one thing that they improved was the elimination of packet loss, and that can operate at 10, 40, or 100 gigabits per second. Then we have fiber channel over IP, which then uses the TCP/IP stack and then communicates across the Ethernet, and that can be a 1, 10, 40, or 100 gigabit type of connection. So now we move over to iSCSI, and iSCSI has two ways that it can connect up to Ethernet. It can go through the TCP/IP stack, similar to fiber channel over IP, and get down to the Ethernet protocol. Again, 1, 10, 40, and 100 gigabits. Or it can bypass it using the TOE, which is the TCP Offload Engine. That's what TOE stands for. And what that's going to do is it's going to move all that processing off of the TCP/IP stack. So it removes that layer of overhead and communicates directly with the Ethernet protocol. So 1, 10, 40, and 100. And you see it says future here. Well, we've achieved some of those speeds. I think we're close to 50 in some places. If you look here at the SRP ISER, okay, that's going to be it's a iSCSI protocol that uses remote direct memory to kind of connect in, and then That's what the SRP is the iSCSI. It allows them through direct devices that directly attach to access each other's memory remotely. And the SRP is what makes the which makes the SCSI protocol a remote protocol. With the IB, I'm sorry, and the ISCR is oh gosh. See, even I have to look some stuff up sometimes because this is just so heavy, and if you don't run into it, you don't run into it. Well, either way, that's for you to learn. That's why you're taking the class. It'll be in the book. But IB is InfiniBand, and that is a relatively newer communications network standard, and it's mainly used in high performance computing or high throughput computing where very low latency is needed. So you can actually see this in supercomputers. It's a way that they interconnect the nodes of supercomputers. You're going to see this in data centers and storage systems so that they get that high performance. And as you guys probably saw from the technical glitches, one of the other protocols is voice over IP. And if you've got lag, that's when you get things like pausing and robot voice. But what that essentially does is that's a protocol that allows us to carry voice over data networks and do so with a lower cost. It also provides resiliency. If a POTS line gets cut, that's kind of the end of the story. You can have many things in a VoIP environment fail and still be able to successfully complete phone calls. It does get rid of POTS. And that's, again, plain old telephone service. Really fancy acronym, I know. Us IT people are so great at our acronyms. And then you have the real-time transport protocol. And that's what's not working great for us tonight, is the real-time transport protocol. So I'm trying to live stream to you guys audio and video, and the video clearly wasn't working. Hopefully the audio is better. But that's the protocol that's actually bringing you this live stream today. And then we have the Session Initiation Protocol, or SIP, and that's a signaling protocol. We also have the Secure Real-Time Transport Protocol, and that's providing that real-time secure VoIP using AES and SHA-1 encryption. Without the SRTP, or RTP only, voice over IP calls could be prone to sniffing. You can also route voice over IP calls across IPsec. So now let's dive into wireless a little bit. So wireless local area networks. They're going to transmit information via radio waves. And radio waves are a form of electromagnetic wave. They can also be a form of light. So you can use light as well to transmit information, but traditionally a wireless local area network, the ones you're going to have at work or at home, are going to be a radio-based network. The most common form of wireless data networking is the 802.11 wireless standard. That's the one that we're all pretty much familiar with. The first 802.11 standard with reasonable security was 802.11i. 802.1 was made to make things connect together very easily and to try to maintain those connections as easily as possible. And so security really was a bit of an afterthought. And it took them quite a few iterations to bring any kind of meaningful security to that standard. So some things to understand about a wireless local area network. There is no way to assure availability. Just like with the CISSP mentor class, when they get taught by me or Evan, apparently there's no way to assure availability or stability. What can happen is interference. Interference from other appliances in your home, interference from other wireless networks in your neighborhood. If you live in an apartment building, that can be especially a dense area where you're going to have potential interruption. So to understand that, because there's no way to assure the availability, any attacker within physical proximity has a whole slew of tools in their toolkit for launching a denial of service attack. That could be just polluting the spectrum with noise, putting up a whole bunch of really noisy networks to just kind of drown out your wireless network. They can dominate the whole spectrum. There's a lot of tools out there for them to use. And so if you've got a critical application, and believe it or not, guys, I'm coming to you on a wired connection because I didn't want to have the issues that we did. But critical applications that you need a reliable network should use a wired connection and not a wireless because it can be knocked offline for a variety of different reasons. So there are some things that we refer to as an unlicensed band. So a band is really just a small amount of continuous radio spectrum. The old days, for those of you on the call on the class here tonight that are old enough to remember the rabbit ears on TVs, that all those TV stations operated within a spectrum. And sometimes if you were just far enough out, you would actually get two channels on the same setting, depending on which way you pointed your rabbit ears. You might pick up the neighboring town's TV channel. Generally, industrial, scientific, and medical bands have been set aside for unlicensed use, so no license is needed from the FCC in order to be able to use them. Magnetic resonance imaging, for example, is going to be using radio waves to scan you. And so that's not governed or restricted by the FCC. A lot of wireless devices and cordless phones are going to be in those ISM bands. So the Bluetooth, the 802.11 wireless. If anybody's still using a cordless phone that is not a smartphone, please let our moderators know because I want a picture of that thing. And in different countries, they use different ISM bands. Two of the most popular ones that are used internationally are 2.4 gigahertz and 5 gigahertz. You do need to know this stuff. So, given all the things I just said about how those wireless signals can be polluted, corrupted, interfered with, one of the ways that they attempt to create some semblance of stability is by hopping across the spectrum, so doing frequency hopping. It's a way to send traffic via a radio band, and it's trying to maximize the throughput while minimizing the effects of the interference. And so it's going to use a smaller number of channels throughout the band, and then it's going to hop through them in a somewhat random order. So it's going to kind of bounce around and try to find the one that's hopefully the least, experiencing the least interference. Then you have the direct sequence spread spectrum, or DSSS, and this is a method for sending, again, traffic across a radio band. And again, this also is designed to maximize throughput while minimizing the effects of interference. But the difference here between FHSS and DSSS is that it's using the entire band at once. So it spreads the signal across the band, where frequency hopping is switching the frequency channels it's using throughout the available band. The direct sequence spread uses the entire band. And then you have the orthogonal frequency division multiplexing, because big words are fun, OFDM. And it's just a newer method of doing the multiplexing. So again, really the goal for all of this is to try to increase my throughput while reducing my interference from other wireless sources. The OFDM also allows for the simultaneous transmission using multiple independent wireless frequencies that do not interfere with each other. And a lot of the AC stuff, and we'll get to that. I've got a slide here in a second that kind of gives you a bit of a look at that. So as you can see, we've got these different standards of 802. So there are various flavors, and again, if you're old enough, you'll remember when Wi-Fi first came out, and if you got 54 megabits, you were probably standing directly next to the wireless router. Because it had a pretty short range, right? 75 feet was about all you could hope for. And then as they began to improve upon that, they went to 802.11b, which gave you a longer range but lower speeds. So then along came G, which the majority of people, if they haven't upgraded their router in the last year or so, are running G. And that's going to give you 54 megabits at 150 feet. Obviously, as we got higher content and 4K video and all these things, we needed more throughput. So along came the N network, the 802.11n. And that gave us 600 megabits per second at 175 feet. So we were closer to actually being able to sit out on our patio and use our computers. And then the most recent one is the AC, and that's going to be 1300 megabits, and it works at 175 feet. And just to give you perspective, these ranges are for indoor use. Outdoor is a little bit higher. I'm not going to go through all the IEEE 802 standards, but you do need to know them, so I encourage you to go back and refer to this slide, and also refer to this in the book. So looking at a little bit of a comparison here across the various flavors, if you will, of the 802.11 protocol, we can see there's some differences in the frequency and band. And we notice that the higher the frequency and band, the more throughput and transmission speed that we seem to get. You know, the 2.4 is great, but it's pretty easy to interfere with it, and there's a lot of devices now. Your wireless mouse is trying to use that frequency. Your wireless controller for your Xbox is trying to use that frequency. So it can make kind of your Wi-Fi a little less than ideal. And then what we did in G, you know, they started to combine bands. And you know, if you have a brand new N router, it actually has the option to combine 2, 4, and 5G together to give you a even greater throughput by kind of splitting that traffic across. So this is the new current standard because it does offer high backwards compatibility. The throughput, pretty high throughput, and it's fairly stable. So now we're going to talk about managed, mastered, ad hoc, and monitor modes. So managed mode is the AKA is the client mode, right? Clients cannot connect to anyone other than the access point when connected. So it doesn't allow them to establish other connections to other wireless devices. They're in client mode, they're in a managed mode. In master mode or infrastructure mode, they can only connect with clients that are in managed mode. In ad hoc mode, you can do peer-to-peer communications without going through a central access point. And then monitor mode is a read-only mode for sniffing out the wireless traffic. And you know, so if you've heard of like a Wi-Fi pineapple or things like that, right? There's various ways to sniff wireless traffic. That sniffing is occurring in monitor mode. Hopefully you guys aren't falling asleep. I know this is a little bit dry and techy, but SSIDs and MAC address filtering. So the Service Set Identifier, or SSID, generally acts as the network name. That is going to be the name of your wireless network. And you can broadcast it or not broadcast it, right? Depends on your appetite for the neighbors knowing what your wireless is named. Wireless clients have to know what the SSID is before joining. So even if you don't share it, you have to know it before you'll be allowed to join the wireless LAN. And in general, they are broadcasted. Some are disabled for security reasons usually. And so there's a bit of a reliance on the secrecy of the SSID, right? That was an old habit. It's a terrible security strategy. A wireless sniffer in monitor mode can pick up those hidden SSIDs. And so don't just assume hiding it, you know, is going to help. MAC addresses are exposed in plain text across the 802.11 on wireless. Trusted MACs can be sniffed, and an attacker could reconfigure a non-trusted device with a trusted MAC address and software. So that's that MAC address spoofing that we were talking about earlier on. Wireless equivalency protocol, which was a really poor attempt to create a stronger form of security, and unfortunately it proved itself to be quite weak. WEP can be cracked in just minutes. It doesn't take very long at all to break a WEP key. There's very little protection to any kind of confidentiality or integrity. It is really discouraged these days to use WEP. It really, if you need additional layers, use a VPN WEP really isn't any good. It's got 40 and 104 bit key lengths, and it uses an RC4 cipher. So this 40, this RC4, this 104, these are red flags for why this isn't necessarily a good protocol. Also, the frames have no timestamp, and there's no replay protection. So these are other replay attacks as another type of attack that could be used. It's widely criticized, again, for all these reasons. It's too small of keys. The initialization vector is too small. It doesn't properly check integrity. It's using RC4. It's a weak encryption. We know that. Authentication messages can easily be forged. So WEP will be in the test. Know that it exists. Please don't ever use it. So 802.11i was the first actual security standard for wireless. It does provide a reasonable degree of security protection. It kind of has the robust security network, which is going to allow pluggable authentication modules. The robust security network, RSN, is going to allow you to change cryptographic ciphers. So as vulnerabilities happen, you can actually go in and make corrections and changes. You're most familiar with RSN under the name WPA2. So as you've gone to log into those Wi-Fi networks, you've seen WPA2, which stands for Wi-Fi Protected Access 2, and that is a full implementation of 802.11i. By default, WPA2 is using AES encryption to provide confidentiality, and CCMP, or Counter Mode CBC MAC Protocol, right? Love all the $10 words, to create message integrity checks. And that's how you're getting that integrity. You're getting that integrity because you're actually checking and inspecting. WPA2 optionally can use the less secure RC4 cipher and TKIP, which is Temporal Key Integrity Protocol ciphers. Again, I would probably stay away from that, but again, you got to know this. It's on the exam. And probably the most used wireless that I'm aware of, Bluetooth, right? All of us are using Bluetooth. Everybody I know is using Bluetooth. It's a IEEE standard, and they flag it as 802.15, and is considered a personal area network. So if you remember back to last week, wide area network, local area network, metropolitan area network, personal area network, right? So PAN. And it uses the same 2.4 gigahertz frequency as a lot of the other 802.11 wireless devices, or which again could be your mouse and other things. You can use it on low power, which is why it's the preferred device for cell phones and ear pods and all these fun things. But that data then transmits over much shorter distances. Versions 2.1 and older operate at 3 megabits per second or less. 3 and higher have higher and faster speeds. It comes in 3 classes of device. You have class 3, which is going to be under 10 meters. Class 2, which is going to be 10 meters, and Class 1 is going to be 100 meters. And they're using a 128-bit E0 symmetric stream cipher, so that's how the cryptography around Bluetooth is working. However, after thorough crypto analysis by very passionate pen testers, it's proven to be quite weak, and the actual strength's 38 bits or less. So that's why we always say disable your devices, disable Bluetooth on your devices if you're not using it. It is relatively easy. And this is another version of Bluetooth. This is the latest version 7.0. Now we're going to talk about RFIDs. So RFIDs are another type of wireless local area network. It is a passive type of network. It relies on the reader to be powered. The RFID itself is not powered in almost all cases. And it was originally, created to have the ability to track wildlife and to track objects. As things move throughout the warehouse, I can keep an eye on it as it moves past the scanner. And the one that we're most familiar with is this badge scanner down here. Most of us have this and use this in our employment. And a lot of us also have the new credit cards that have the RFID or wireless built into it. If your credit card has these lines on it here, look like the Wi-Fi lines, that indicates that card is RFID enabled, and you can use it on those touch readers. So we have these 3 different types. Now, you have an active RFID, so that's going to be powered. right? That's an active tag. That's what they're going to clip on to a bear up in the woods that they caught. That's what they're going to use on objects that they need to know that it's broadcasting at all times. It can operate over larger distances. Toll transponders, if you have those in your car, if you have that little thing for the fast pay lane or the toll lane, that's using an active RFID. Semi-passive is going to have a battery, but they're going to rely on the reader's signal for that extra power. And then passive doesn't have any battery at all. So that badge for work, or the RFID chip that you put in your dog to find them when they run away, those are passive. Tracking inventory in a warehouse is another example. Then we have ways to block those RFIDs. So maybe you've seen all the TV commercials about the blocking of the RFID in the wallets. You see we have an example here, RFID wallet. But signals can be blocked. All radio signals can be blocked with a Faraday cage. And a cage can be as simple as aluminum foil wrapped around an object. It can be as fancy as a metal cage. If you want to build your own Faraday cage wallet, you can follow this link to how to make one. There's also tons of them available online. And if you're really paranoid, I recommend this. This is a great way to keep the spacemen out of your brain and to keep those RFID signals from leaking out. So, network devices and protocols. We're now going to dive into repeaters and hubs. Hopefully you guys are doing good. Let the moderators know if I'm moving too quick or not quick enough, and hopefully everybody's still awake. So layer 1 devices, the repeater receives a bit on one port, and then it repeats it out to another port. It doesn't understand protocols, it just repeats bits. Kind of like a small child. It'll repeat things you say without necessarily understanding context. Repeaters are generally used to extend the length of a network because we do have limitations, physical limitations, in how long of a cable we can run before we see a degradation of signal strength. So repeaters are used to boost that signal strength. A hub is a repeater that has 2 or more ports on it. And hubs receive the bit on one port and then repeat them across all ports. There's no traffic isolation and there's no security. All nodes are sent all traffic. Hubs are done. Half duplex, so if you remember from last week, half duplex, full duplex. Half duplex cannot send and receive simultaneously. Full duplex can send and receive simultaneously. So you have collision issues. So you can have a collision domain and any node may send colliding traffic with another. So you really don't want to use a hub these days, but repeaters are still very much in use. And here's a visual example. It takes that weakened signal that's had degradation and it boosts it back up to a nice strong signal. Now we have bridges. And bridges are layer 2 devices and they have 2 ports that connect network segments together. So it's exactly like a physical bridge, right? The idea is that you're spanning a gap. And it's going to provide traffic isolation and it makes forwarding decisions by learning the MAC addresses of the nodes connected to it. It has 2 collision domains to handle those issues. This is a image of kind of what it looks like. So again, it's a bridge. I'm connecting one segment to another segment, and I'm using a bridge to do that. Now a switch, and I don't know why that's showing like that. Let me go back here. For some reason that popped up wrong. But a switch is going to be a bridge with more than 2 ports, right? It's going to shrink the collision rate. It's going to use trunking and other things to help. And I'll correct this when I send the slides out. I don't know why this one is off like this, but basically, think of it as like a smart bridge, if you will, right? It's going to provide traffic isolation relative to the server and port that it's trying to route things to, and so. That's what it's doing. And a VLAN is a virtual switch. That's really at the end of the day what it is. So we always say to use VLANs. So VLAN's just another way of switching. It's a way for us to get more out of a physical switch by creating virtual LANs within it. And then inter-VLAN communication requires you to use layer 3 routing. So you can't use layer 2 routing when you're trying to negotiate and navigate this. You got to do it across layer 3. So that moves us to span ports. So span ports and mirroring, right? Span is a term that was coined by Cisco to describe how this works. HP decided to use the term mirror port. because, hey, let's make this really easy to understand. It's just mirroring that. You're using it for intrusion detection prevention, right? So I'm mirroring all the traffic, or I'm spanning all the traffic that's coming in on one switch out to another, so that I can do something with that. I can use that for IPS IDS. I can use that to inspect, suspicious traffic. One of the drawbacks to using a span port is that you can get port bandwidth overload. And then you have test access ports, or TAPs. And it's a way to tap into the network and see if all the unicast streams, and to be able to see them on the network. This is very common in the world of security, to use a tap to gain access to the network and pull that off. That's where we'll put sniffers and other network intrusion detection systems. You could even tap your SIM into the environment. They will fail open. Or they can fail open rather, and that will allow the network traffic to pass through even if there has been a failure. Now, a hub or a switch span port will not do that. They will generally fail closed. Routers are going to be layer 3 devices, and they route that traffic from one LAN to another. IP-based routers are making their routing decisions based on source and destination IP addresses. And in the real world, one chassis such as a Cisco 6500 can be many devices at once. It can be a router, a switch, a firewall, network intrusion detection, etc., etc. The exam is going to give you more clear cut. It's going to say things like a dedicated firewall, a dedicated switch. If the exam is referring to a multifunction device, they will make that clear. So it's helpful to understand and think of these things as distinct concepts, even though in the real world as one physical device. Static and dynamic routes. So static routes are fixed routes to other networks. Generally, they're manually entered into the routing table, and they're good for simple routing needs and fixed networks. So if you don't need a lot of redundancy, and you want to make sure that box A always talks to box B with no one possibly being in between, you're going to use those static routes. You could use default routes, but a default route does not necessarily know the route to the other network. And if there are no other routes to use, then it will use the default route. So if you haven't set up routes, it will just kind of use a default. Okay? And again, big key here, static route, default route. So routing requires protocols. And automatic routing is how that happens is going to be dependent on the protocol in use. So when we talked about convergence before, right, this is when all the routers are in agreement on how they're going to route. So they've synchronized their routing tables, they've synchronized their topology, they understand how to communicate with each other and make sure that the same routes are followed. Then you have the Interior Gateway Protocol, or the IGP. Okay, and this is part of the open shortest path first and enhanced interior gateway routing protocols. Okay, these are interior gateway protocols, and we'll get a little bit more into RIP here and OSPF in a minute. And then you have the exterior gateway protocols, and the biggest, most well-known one of that is the border gateway protocol. That is kind of the king protocol, if you will. So distance vector routing protocols, it basically is going to inform its neighbors of any topology changes, and it's going to do that periodically. If you guys remember ARPANET, the old ARPANET routing algorithm, or the Bellman-Ford algorithm, this is just kind of the new school version, right? And distances are based on a chosen metric and computed using the distance information from their various neighbors. So they get these distance vectors and figure that out. So those metrics are used to then determine the best route across the network. And the simplest metric is hop count. So how many hops, how many devices do I have to go through to get from my source to my destination network? It's not going to account for link speed in between those networks, and it is prone to rerouting loops, where it can become kind of trapped in a reroute loop. RIP, so like I said, we talk about this in a second. This is the Routing Information Protocol, and is one of the oldest distance vector protocols that employs hop count routing as a metric. And RIP's going to prevent routing loops by implementing a limit on the number of hops allowed in a path from a source to a destination. So it's using that hop count. It's saying if it's more than 30, give up. it cannot see or have full view of the network. It can only see the directly connected routers. It is slow. Convergence is slow. It sends routing updates every 30 seconds, even if there's been no changes in the routing. Maximum hop count is 15, and 16 it considers to be infinite. So, again, if it can't get what it's looking for soon enough in a number of hops, it shuts down. RIP v1 can route classful networks only, and RIP v2 added support for CIDR. It uses split horizon to avoid those routing loops. So it's not going to argue, right? The easiest way to think about split horizon is not going to argue back. It uses a hold down timer to avoid flapping, which is repeatedly changing the router status from up to down. More routing protocols. Automatic routing is again going to be based on the protocol used. So notice that showed up on a couple slides. That one should definitely be something you're locking away in your brain. Link state routing protocols provide additional metrics for determining that best route. And OSPF is an example of that, and it can use bandwidth, congestion, and other metrics for routing decisions. So what is OSPF? So that's open shortest path first. How quickly can I get from point A to point B, and is there an open route for me to do that? It's a link state routing protocol. And so the router learns the entire network topology for their area, and that's the portion of the network where they maintain routes, usually the entire network for small networks. Routers are then send event-driven updates, so they receive updates on things that are happening. This is far faster than convergence, than distance vector protocols such as RIP. So OSPF is definitely going to give you the speed because it's looking for the fastest, shortest path that's open. Static and default routes. So static routes don't change. They stay the same. Default routes can go different directions. Default route could take this one path, this other path, the next path, right? But a static is going to follow the same path. That's the big thing to know here, right? Is static doesn't change. Default is going to be there if there's no other routing present. So then we're going to talk about Border Gateway Protocol. And this is the routing protocol that's primarily used on the internet. It is a standardized exterior gateway designed to exchange routing and reachability information among autonomous systems on the internet, right? So it's saying, hey, what's going on out there? Let me know what's happening. I need to do routing. And so it routes between autonomous systems, which are basically networks within multiple internet connections. It has some distance vector properties, but it is formally considered a path vector routing protocol. Now again, you'll see the note here. There's a reason we haven't dove into proprietary routing protocols, and the biggest reason for that is that the exam isn't really going to ask you about that. It's going to focus on those open routing protocols. So firewalls. So firewalls, I think probably everyone is familiar with, but their main job is to filter the traffic between networks. So either blocking that traffic or routing that traffic or doing something with it, right? And generally a firewall is going to be placed, at least the first one, in between the outside world, aka the internet, and the inside network. And then you can have many, many more firewalls from there, right? The most secure organizations run lots of firewalls at different stages within the networks. TCP/IP packet filtering and stateful firewalls make decisions based on layer 3 and 4, so IP address and ports. Proxy firewalls are able to make decisions up at layers 5 and 7 of the OSI. Firewalls are multi-homed and they have multiple NICs connected to multiple different networks. Okay? And we think of firewall, a lot of times we think of this. Once you work in the business long enough, you realize most people's firewalls look a lot like this. So packet filtering is a type of firewall. And it's simple and it's fast. It has no concept of state. Each filtering decision has to be made on the basis of a single packet. So what do I do with this packet? Not what came before it, not what comes after it. There's no way to refer to the previous packets to make current decisions. So a lack of state makes packet firewalls less secure, for the session, and protocols like UDP and ICMP, right? So the lack of having a state ultimately makes it less secure because it doesn't know what happened before or after. And if you're using sessionless protocols, that could be even more challenging. So here's an example visually of what that packet filter is going to kind of look like, right? So we're going to have the packet filter firewall. Computer 1 is sending its ICMP request. It's getting its reply. And then somebody could send a spoofed reply. And you can see here this evil bad person is sending spoofed replies. Stateful firewalls. They maintain a state table that's going to allow you to compare what came before, so you can look at previous packets. It's going to be slower because it's doing that inspection, but it is far more secure. It's basically tracking the operating states and characteristics of the network connections that are traversing it, right? It's looking for legitimate network packets and trying to distinguish them from packets that maybe are not as legitimate or there's no state data for it to compare to. So it's only going to let through packets that are matching a known active connection. So again, a stateless firewall has no context. A stateful firewall has context. Then we get into proxy firewalls. And proxy firewalls are part of the greater network security system that's going to help keep those network resources safe by filtering messages at the application layer. You maybe have heard of these as an application firewall or a gateway firewall. But it essentially is a proxy firewall, and it acts as an intermediary. And proxies terminate connections. So it's able to, as you see from the graphic here, a stateful firewall, while it has context, is letting things flow through. A proxy firewall is stopping things and then routing them through. So you're going to see that here, right? So that's operating up at layer 7. And it's going to make its filtering decisions based on application layer data. Is it HTTP traffic, HTTPS traffic? What type of traffic is it? It's going to look at layers 3 and 4. It needs to understand the protocol that is proxied. So dedicated proxies are often required for each protocol. FTP, for example, HTTP proxy for web traffic. And that's going to allow for tighter control of the filtering decisions. Proxy firewalls are pretty good and pretty common in mature organizations. So you have circuit level proxies. So this is the SOCs. This is going to operate at layer 5, so it's going to be down at that session layer. And it's going to allow circuit level proxies to filter more protocols. They don't need to understand each protocol. The application layer data is simply passed along. And the most popular example of a circuit level proxy is the SOCs. It uses TC port 1080, and some of the applications must be SOCsified to pass through a SOCs proxy. The current version is SOCs 5. It is not able to make filtering decisions based on the application layer data, such as explicit web content. That's going to be, back up at layer 7, or additional content filtering, things like that. Then you have dual home hosts. So this is kind of get into the fundamental firewall designs. Dual home host or dual homing is referring to either an Ethernet device that has more than one network interface for redundancy, or in a firewall, it's that one of the firewall architectures for implementing preventive security. And in this case, this is about preventive security. So 2 network interfaces, one is connected to a trusted network and the other is connected to an untrusted network, such as the internet. The host does not route. A user wishing to access the trusted network from the internet would log into the dual home host first and then access the trusted network from there. This is a common design before the modern firewalls. So back in the 90s, this is kind of how we did it. Modern firewalls kind of eliminated the need for that. And then you have a screened host architecture. So this is an older flat network design using one router to filter external traffic to and from a bastion host via an access control list, so an ACL. The bastion host can reach other internal resources, but the router ACL forbids direct internal-external connectivity. So it's checking that ACL to see if it's allowed. a screened host provides, instead of using a separate router, it allows that to happen within the internal network, depending on how you set up a screened host. DMZ networks and screen subnet architecture. So again, older flat network design use one router to filter external traffic to and from a bastion host via an ACL, access control list. The bastion host can reach other internal resources, but the router ACL forbids direct internal-external connectivity. A screen subnet, also known as a triple-homed firewall, uses a single firewall with 3 network interfaces. Interface 2 connects to a DMZ, which hosts public services. Interface 3 connects to an intranet for access to and from internal networks. So that's just a little bit more about that. Fundamental, so DMZ again. DMZ stands for Demilitarized Zone or Demilitarized Network. The hosts that receive traffic from untrusted networks, such as the internet, should be placed on the DMZ networks. And it's designed with the assumption that any DMZ host may be compromised. The DMZ is designed to contain the compromise and prevent it from extending into the internal trusted networks. DMZ is part of assume breach mentality, right? We're assuming that the host is potentially compromised, and if it's not compromised, there's a good chance it may be compromised. And we're okay with that because the DMZ is preventing that from actually entering that internal trusted network. You should absolutely harden your DMZ host. So any host that you have in the DMZ should be hardened because, again, the assumption is the DMZ may be compromised. DMZ networks and screen subnet architecture. So a classic DMZ is going to use 2 firewalls. As you can see in the example below, we have the internet, you have an external firewall, then you have your web server, email server, and FTP server, and then you have an internal firewall before you get to the trusted internal network. And that's a good design. That's the classic design. A single firewall DMZ uses one firewall, sometimes called a 3-legged DMZ. You can do this. Hopefully you don't have to. Hopefully you can put that second firewall in, not just for redundancy purposes, but it's just a better practice. Single firewall designs require that the firewall can filter traffic on all interfaces, untrusted, trusted, and DMZ. Dual firewall designs are more complex, but they are more secure. And the term DMZ alone implies that it is a dual firewall. So if people are talking about DMZ in the 2020 context, they're going to be talking about it as a dual firewall, not a 3-legged. Modem. This is a little bit of a jump in the time machine. So modem, or modulator demodulator, took binary data and it modulated it into analog sound. That beautiful, beautiful sound that we heard when we would pick up the phone in the 90s and somebody in the family was browsing AOL chat and we would get that lovely screeching, screaming buzz in our ear. That was the binary data being modulated to analog sound. And that was done to allow it to be carried across the phone networks that were designed to carry human voice. And then the receiving modem would demodulate that, so it would decode it, and back to binary. So it would take all those screams and screeches and turn them into ones and zeros. They are asynchronous devices. They do not operate with any type of clock signal. This is an example of one of the old school modems. And for those of you on the class tonight that actually used or had one of these, let us know in the chat. I'm curious to see how many of you have ever used or seen one of these. DTE, DCE, CSU, and DSU. Oh, acronyms, acronyms, acronyms. DTE is data terminal equipment, or is a network terminal. It's any type of network-connected user machine, desktop, server, or an actual terminal. They still exist in the world and they are still used. DCE is data circuit terminating equipment, or sometimes called data communications equipment. And that's a device that's going to network DTEs together. So a router would be a DCE, your laptop would be a DTE. The circuit carries the DCE DTE. The circuit that carries that is synchronous because it does use a clock signal. So modem, no clock signal. DCT DTE, clock signal. And both sides must synchronize to a clock signal provided by the DCE. The DCE device is a modem or a CSU DSU, so channel service unit or data service unit. The more common use of these terms and the meaning of each is a little bit more like this. So DCE marks the end of the ISP's network connecting to the DTE, so the data terminal equipment, which is the responsibility of the customer. The point where the DCE meets the DTE is called the demarc or demarcation point. That is where the internet service provider's responsibility ends and the customer's begins. And if you've ever had to hunt through an old building to find the demarc, that can be quite a fun activity. Authentication protocols and frameworks. So authentication is an identity claim. It authenticates an identity claim over the network. It is good security design. Assumes that a network eavesdropper is going to sniff all packets sent between the client and authentication server. So the protocol should remain secure. You don't want people sniffing your authentications. So PAP and CHAP. PAP, Password Authentication Protocol. It is very weak. It sends the username and password in clear text. And frankly, you just shouldn't use it. It's some leftover legacy stuff that is best served in the burning porta potties I showed you earlier. And then CHAP, which is Challenge Handshake Authentication Protocol. So it's more secure. It's not exposing passwords in clear text. It is not susceptible to replay attacks. It does rely on a shared secret, the password. And the password is securely created, so like when you're setting up an account, for example, and it's stored on the CHAP server. Since both the user and the CHAP server share a secret, the plain text password, they can use that secret to securely communicate. The server stores plain text passwords of each client, and so that's a weakness in CHAP. So CHAP is going to, to authenticate, it's first going to create an initial unauthenticated connection via the LCP, or the Link Control Protocol. The server then begins the three-way CHAP authentication process, or the handshake, if you will. The server sends a challenge, which is a small random string, also called announce. The user then takes the challenge string and the password, uses a hash cipher such as MD5 to create a hash value, and then sends that value back to the CHAP server as the response. The CHAP server also hashes the password and challenge, creating the expected response. It then compares the expected response with the response received from the user. If both of the responses are identical, the user must have entered in the appropriate password and is then therefore authenticated. If they are different, the user entered in the wrong password and access is denied, and you get that fun little pop-up. This is another type of CHAP, who might also be a PAP. Who knows? 802.1x and EAP. So 802.1x is a port-based network access control. It includes the Extensible Authentication Protocol, or EAP. I don't know about you guys, but at this point I'm pretty much choking on alphabet soup. EAP is an authentication framework that describes many specific authentication protocols. It was designed to provide authentication at layer 2 before a node receives an IP address, and it protects against the roaming infected laptop. It is available both in wired and wireless, but is most commonly deployed on a wireless local area network. And each EAP client is called a supplicant, which requests authentication from an authenticator. I'm just going to check in with my moderators here. We on track? We're doing good. I don't see any messages, so cool. 802.1x and EAP. So EAP has different types. There's LEAP, which is the Lightweight Extensible Authentication Protocol. This is a Cisco proprietary protocol that was released before 802.1x was finalized. There are significant security flaws and you should not use it. However, it's probably going to be something you need to know, so when you run into it, you know how to use it. EAP and TLS. So that's EAP, Transport Layer Security, and it's going to use a public key infrastructure requiring both server-side and client-side certificates. It establishes a secure TLS tunnel used for authentication. It is very secure because it's using the public key infrastructure, but it is more complex and costly for the same reasons. You have EAP Tunneled Transport Layer Security. So this was developed by Funk Software and Certicom, and it simplifies the EAP TLS by dropping the client-side certificate requirement, allowing other authentication methods such as passwords for client-side authentication. It's easier to deploy than EAP TLS, but less secure when omitting the client-side certificate because you don't have those two certificates, so you're inherently a little bit less secure. And then there's PEEP, which is Protected EAP. And this was jointly developed by Cisco, Microsoft, and RSA. And similar to, and potentially a competitor of, EAP TTLS, including the piece of not requiring those client-side certificates. VPN is going to be that virtual private network, and secure data is sent via it's getting late. It is to secure data sent via insecure networks such as the internet. Really the idea of a VPN is that I create this magic wrapper that allows me to send my data down a dedicated secured protocol. So the goal is to provide the same level of privacy that you would have if you had a physical line such as a T1 or unbroken fiber or something like that, but to do so virtually. Then we have SLIP and PPP. So SLIP, Serial Line Internet Protocol, is a layer 2 protocol, and it's providing IP connectivity via an asynchronous connection such as serial lines and modems. It was introduced in 1988 and allowed for routing packets via modem links for the first time. So previously to that, modems were used for non-routed terminal access. It provides no built-in confidentiality, integrity, or authentication, and it was largely replaced with PPP. And PPP is that point-to-point protocol. So again, this is a layer 2 protocol, and it basically got rid of SLIP, and it's based on HDLC, if you remember that from about a dozen slides ago. And what it does is it adds confidentiality, integrity, and authentication via point-to-point links. So again, having those synchronous links, such as a T1, but it also then supports asynchronous links, such as modems. And then there's point-to-point tunneling protocol, or PPTP. And that's going to do PPP via IP. So I hope you guys are keeping up. There's jokes in here I can't tell. Developed by a consortium of vendors, including Microsoft, 3Com, and others, it uses the generic routing encapsulation to pass the PPP via the IP and uses TCP for control channel using TCP port 1723. Somebody, for God's sakes, make a TikTok of you reading all this stuff out loud while dancing. Then we have layer 2 tunneling protocol. So that's going to combine the PPTP and the L2F, so the layer 2 forwarding that was designed to tunnel the PPP. And that's going to focus on the authentication. It does not provide you with confidentiality. It is frequently used with IPsec to provide encryption. L2TP can also be used on non-IP networks such as ATM. And then VPN. Well, VPN IPv4 has no built-in confidentiality. So IPsec was designed to provide confidentiality, integrity, and authentication via encryption for IPv6. They have since ported IPsec to IPv4. And IPsec is a suite of protocols. The major 2 protocols are the Encapsulating Security Protocol, or the ESP, and the Authentication Header, or the AH. Each IP protocol number, ESP is protocol 50 and AH is protocol 51. So each IP protocol is going to have a number associated with it. The 2 major ones you need to know are ESP and AH. There are a ton, however, that are here. So I encourage you to study this graphic. It's a lot, but it's really going to help you put all of those things that we just talked about into kind of some perspective. You can see where the layer 2 frame is. You can see how IPsec rides atop of that TCP UDP is riding on top of that, and then you have your upper layer messaging, with layer 1 obviously being the physical layer where the ones and zeros live. So IPsec has 3 architectures to it. You have host to gateway, or client mode, and that's used to connect one system, which runs IPsec client software, to an IPsec gateway. So host to gateway. Gateway to gateway, or point to point, connects 2 IPsec gateways, which form an IPsec connection that acts like a shared routable network connection. And then host to host. So this connects 2 systems, such as file servers, to each other via IPsec. Mainly modern operating systems can run IPsec natively, and so they can form those host to gateway or host to host connections. Basically, if you're running anything made in the last couple of years, that's going to just be inherent in it. But your takeaway again is host to gateway to gateway, and host to host. Again, orange. You really want to make sure that that gets locked away in your brain. So anything in these slides as you're studying the next couple days, make sure if it's orange to really, really focus hard to remember it. So SSL and TLS. So Secure Socket Layer was designed to protect the Hypertext Transfer Protocol, or HTTP data, because that was all flying around in plain text. HTTPS, which is HTTP with SSL applied, routes across port 443. So again, it's important to know HTTP is port 80, HTTPS is port 443. And then you have TLS. And TLS, which is Transport Layer Security, is really intended to replace SSL. SSL 3 was deprecated in June of 2015 due to a host of security issues. TLS is now considered kind of the de facto standard, and the current version of TLS is 1.2. And if you follow this link, you can see a more in-depth. I think they've actually released 1.3 already, but I'd have to double check. You can use it to tunnel other IP protocols to then form VPN connections. SSL VPNs can be simpler. SSL client software is not going to require altering of the operating system, so it's much easier for your end users to use. IPsec is difficult to firewall. SSL is far simpler. So there's a lot of advantages to that. And then here you can see kind of in the green, what do we got going on? So we've got our SYN and our SYNAC, and then our ACK, our acknowledgement, right? Now we have an established connection, and then the SSL protocol is going to do the hello, right? So it's going to send a hello from client to server. Server's going to respond back, hey, how you doing? Then we're going to share this master secret that we've shared in advance, and then that's going to allow us to create the session key. And then we're using the master secret to generate symmetric session keys. So then we do all the stuff we do here. This is our session. Okay, now when we're done, we go to close the session. We send client finished. I don't know why they call it a hello up here and don't call it a goodbye down here. It would make way more sense, but it is what it is. So the client's finished, and then the server comes back and says, I'm done as well, and then messages that need to be exchanged are exchanged. Okay. ISDN, Integrated Services Digital Network. It was an early attempt to provide digital service via copper pair. So they were trying to get the POTS lines that they had already run all over the nation to be able to handle this. And so they came up with this ISDN. And the devices that use it are called terminals. It uses basic rate interference, the service, and that service provides two 64 kilobit digital channels plus a 16 kilobit signaling channel via the copper pair. And then you have PRI, which is primary rate interface, and that provides 23 64K channels plus one 16 kilobit signaling channel. So your takeaways here, ISDN, know it, it's orange. And there's some flavors, BRI and PRI. Basic rate, primary rate. 2, 23. So these are the key things to kind of remember from this as you prepare for the exam. Then we have DSL. So that's our digital subscriber line. That's the last mile, right? So similar to ISDN, it's using copper pairs to provide digital service to the home. And as a general rule, the closer you physically are to the central office, the faster the service is that you're going to get. So you'll get better bandwidth the closer you are to the main connection that DSL ties back to. Some of the common types are symmetric digital subscriber line, or SDSL, that has matching upload and download speeds. You have asymmetric DSL, so it's going to give you faster download speeds and upload. ADSL is what you're most commonly going to find in someone's home if they have a DSL service being provided by their telecommunications, right? So if they, in my neighborhood, we've got CenturyLink, and if you get a DSL from CenturyLink, it's an ADSL. Then you have the very high rate digital subscriber line. So that features much faster asymmetric speeds. Then there's high data rate DSL, which matches SDSL speeds using 2 pairs of copper. HDSL is used to provide inexpensive T1 service. So again, I don't know a whole lot of people still rocking T1s. I do know they're out there and they exist. So this helps you to understand a little bit of the type of DSL, what you can expect in download speeds, upload speeds, and kind of when that starts to fall apart. So if you're more than 18,000 feet away, you're probably going to start to see drops in these speeds if you're using an ADSL. If you're SDSL, it's 10,000 feet, ADSL is 10,000 feet, and VDSL is actually less than 5,000 feet, but you can get up to 20 megabits a second across it for upload speed and 20 to 50 megabits in download speed. Cable modems. Cable modems are provided to us by our cable TV providers, and they're allowing us to get internet access via the broadband cable TV. So if you've got that coax connection, you've got that cable TV wire coming to your house, that's going to plug into that cable modem and provide you internet access across the exact same wire that all those TV channels are on. And that's because it has multiple channels. So broadband, unlike baseband, has multiple channels available to it. Dedicating bandwidth for network services requires dedicating channels for that purpose. So unlike DSL, cable modem bandwidth is typically shared with your neighbors on the same network segment, which is why I think I was having internet issues earlier. Callback and caller ID. So callback is a modem-based authentication system. The user connects via a modem and authenticates. The system then hangs up and calls the user back at the pre-configured number. Caller ID is a similar method. In addition to username and password, it requires calling from the correct phone number. Caller ID can easily be forged. Many phone providers allow the end user to select any caller ID number of their choice, and so it makes caller ID a very weak form of authentication. Instant messaging. Oh, instant messaging. AOL Instant Messenger sucked up a lot of my time in life. So did ICQ, right? So allows 2 or more users to communicate with each other via real-time chat. And this is very, very popular. We use it all the time. Facebook, I mean, there's a million different, instant messaging apps out there. WhatsApp, you name it. And chat may be one-to-one or one-to-many if you're using chat groups. In addition to chatting, most modern instant messaging also allows for file sharing, audio-video conferencing. Most of us today are using some type of this in our workplace, and all of you are currently using instant messaging to talk to us through the chat window. Other chat protocols and networks, we had AOL Instant Messenger, or AIM, ICQ, which was short for ICQ. You have Extensible Messaging and Presence Protocol, used to be known as Jabber, now it's XMPP. Organizations really need to have a policy around controlling the use of chat software, and you should have technical controls in place to monitor it and, if necessary, block their usage. So this is a really important bullet point, right? So why did we just talk about instant messaging? Well, instant messaging could be a vector of security issues for you and your organization. So know about it and know that it needs to be secured and monitored. Internet Relay Chat, or old IRC. It is a global network of chat servers that was created in 1988. It is still very popular. It's popular with good people and bad people. So IRCs use TCP port 6667 by default. However, many IRC servers can run on non-standard ports, so you can configure that weird high number port and use that. IRC can be used for legitimate purposes, but it also is used by malware to phone home. And it can call home and get those command and control commands via an IRC. So it's important to understand that this exists because if you see that IRC traffic happening in your environment, that could be an indicator that you have some type of malware that's maybe communicating home. It could also just be that you've got an old hardcore geek on the IT team that still uses IRC to talk to his friends or her friends. Remote desktop console access. It's been around a really long time, right? RLogin, RSH, and NIX, right? Operating systems had very poor security, clear text. TCP 513 and 514 are the ports. Virtual Network Computing, or VNC, if anybody remembers that, uses TCP 5900. And then the one we're probably all most familiar with is RDP, or Remote Desktop Protocol, and that's going to use TCP port 3389. We are a little bit early, so I will take a few questions. Hopefully this was not too terrible. You guys learned some stuff. Your brain isn't completely fried from acronyms. We're going to have our next class on Monday. Evan's going to be leading that one, so bring your questions. And I'm just going to pause for a minute and see if the moderators have any questions from the chat that I can answer. All right, doesn't look like we've got a whole lot of questions tonight, so either I did a really great job or all those acronyms put you to bed, but either way, I really appreciate you guys attending the class tonight. It means a lot to Brad, to Evan, and to myself to be able to do this for you guys, so we appreciate your continued attendance. Please do like this on YouTube. It helps us to get exposure. Feel free to share this with people. And I look forward to talking to you guys next week. I'm going to leave this up for just a few minutes before I end the stream. But with that, I bid you all a great night, and I will talk to you soon.